Hey guys, my name is IBM and I am recording the last paper for October-November 2024. These are multiple choice questions. Do not forget to visit our website www.cieresourcemaster.com where you can find many of these resources. Many resources are being uploaded and many will be there with the time. So without wasting time, I'll just go to the first question. I'll not read through the instructions. They are the usual instructions. So question number one, which statement about physical quantities is correct? We know that a physical quantity should have a unit and a magnitude, which is the size. So a physical quantity does not always have a magnitude or a unit. This is not correct. It should always have a unit and a magnitude. A physical quantity must always have a magnitude but does not always have a unit. A physical quantity must have both size and unit, or magnitude and unit. A physical quantity must always have a unit but does not always have a magnitude. It must have both. So the answer is going to be D. A physical quantity must always have a magnitude and a unit. A magnitude is the size. What is a reasonable estimate of the mass of a solid sphere of copper that has diameter 60 centimeters? So the easiest way to do this, we are going to check the densities which can be given by these masses and see if they are reasonable densities of copper. So we know that mass equals density times volume, and for a sphere, volume is going to be 4 over 3 pi r cubed. Of course, radius, this is going to be the same as 4 over 3 pi. The radius is diameter divided by 2, but this is power 3, which becomes d cubed over 8. The 8 cancels, so it becomes pi d cubed divided by 6. That is the volume. Therefore, it means the mass. It means the mass is going to be equal to the density, which is density times pi d power 3 divided by 6. So if I want to estimate the density is going to be 6 times of the mass, 6m divided by pi d cubed. So I'm just going to check to see which densities are given by these masses. I'm substituting this equation here for each of the mass given. The diameter, of course, is the same, 60 centimeters. I'll just change this to meters, so it will be 0.6 meters. So I'm just going to substitute this equation to find the the density given by each of these. The first one, the mass is 0.1. So it is going to be 6 times 0.1 divided by shift pi divided by diameter, which is 0.6, but this is cubed. So that is 0.88. So the density given by this one is 0.88 kilograms per meter cubed. This is even less than the density of water. So copper cannot be less dense than water. So that is wrong. Let's check the second one. The second one, we are going to have 6 times 10 divided by pi times 0.6 cubed. So that is 88. So this is 88 kilograms per meters cubed. It is still less than the density of water. Copper cannot be less dense than water, so that is wrong. Let's check the next one. The next one is 1000 times 6 divided by pi times 0.6 cubed. So this is 8842. This is 8842. This is already dense. It is about 9 times denser than the density of water. Remember, the density of water is about 1000 kilograms per meters cubed. So I think this is making sense. 8842 kilograms per meters cubed as density, that is good enough, and this is going to be extremely large, so you can take a C to be the density of. What is the reasonable estimate of the mass of solid sphere? Because this is giving us a density of approximately 9 times the density of water, then the reasonable mass of a solid sphere should be 1000 kilograms. The power output P of a star can be modeled with the equation power is sigma AT power 4, where sigma is a constant, A is surface area, and the units are meters squared. T is temperature, the units are Kelvin. What are the SI base units of sigma? So making sigma the subject, sigma is going to be power divided by area times T to the power 4. And we know that the power is equal to energy over time, or work done over time, or force times distance divided by time, which gives us the units as kilogram meters squared s power minus 2 divided by s. That is kilogram meters per second squared times meters over s. So the units of power are actually kilogram meters squared s power minus 3. So the units of sigma are going to be equal to kilogram meters squared s power minus 3 divided by area, which is meters squared, and temperature power 4, which is Kelvin power 4. So this cancels, and this simplifies to kilogram s power minus 3 Kelvin power minus 4, which makes the answer to be B. A boy throws a stone with a horizontal velocity of 10 meters per second from the top of a building. The height of the building is 80 meters. The stone travels along a curved path until it hits the horizontal ground as shown. Air resistance is negligible, which means the acceleration in the vertical is constant and is equal to g. How long does it take the stone to reach the ground? So I'm going to just consider s, displacement in the vertical, equals to initial velocity in the vertical times t plus a half, acceleration in the vertical times t squared. So I'm considering vertical motion, that's why I'm putting subscript y. Vertical displacement is 8. Initial velocity is in the vertical is 0 because it was moving horizontally. So 0 plus a half times 9.81 times t squared. So t is going to be equal to the square root of 2 times 8 divided by 9.81. So 2 times 8 divided by 9.81, square root of the answer, that's 1.277, which is approximately 1.3 seconds. So the answer is C. 4 cuboids with identical lengths, breadths, heights are immersed in water. So they have the same height. That means the difference in pressure on the top and the bottom is going to be the same, because difference in pressure only depends on the height. The difference in pressure is the density of the liquid times g times height of the object. Because the height h is the same for all, the difference in pressure between the top and the bottom of the object is the same. So difference in pressure is the same for all. Cuboid W is made of a material of density 4 rho. X is made of material density twice rho. Y is made of material density rho. Z is made of material 0.5 rho. Which statement is correct? The upthrust. It's all about upthrust. So upthrust is equal to cross-sectional area times difference in pressure. Because all the dimensions are the same, the cross-sectional area is also the same. The difference in pressure between the top and the bottom is also the same because it depends on the density of the liquid, not the density of the cuboids. Because upthrust is equal to area times difference in pressure between the top and the bottom of the object, which is the same as the weight of liquid displaced. And the weight of the liquid displaced depends on the density of the liquid displaced. So the upthrust is going to be the same. So the upthrust of water on each of the cuboids is the same. So the answer is A. In which example is it not possible for the underlined object to be in equilibrium? Remember, for equilibrium, torque, the resultant moment should be equal to 0. The resultant force should be equal to 0. An aeroplane climbs at a steady rate. Steady rate means the height increases. It is climbing at a steady rate. That means that the change in the height with the time is constant, which means the velocity is going to be constant. Velocity is the change in height with the time is constant, which means the velocity is so because it is climbing at a steady rate, then the velocity is increasing. The velocity is increasing at a constant rate, so it means this is not in equilibrium because the resultant force is not 0. That's why it is able to climb at a constant rate. So this one is out. An airplane tows a glider at a constant altitude. At a constant altitude, is towing a glider at a constant altitude, which means there's a resultant force in the horizontal. So this means this is not in equilibrium. A speedboat changes direction. There's a change in direction, but at a constant speed. At a constant speed, it means the acceleration is 0. So the resultant force is going to be 0. And therefore, the answer is going to be C. At a constant speed, the resultant force is 0. Therefore, it is going to be in equilibrium. Two boats tow a ship into a harbor. Therefore, there should be a resultant force in this case, to tow a ship into a harbor. Two identical balls are projected vertically upwards from the ground with the same initial velocity. Which statement about the motion of the balls is correct? Ball X reaches greater maximum height and in a longer time than ball Y. So we have ball X. Let's say this is ball X. Ball X is in a vacuum. So let's say this is ball X. So this is ball X. And ball Y is in air. So let's have ball Y here. This is in a vacuum. This is in air. So the ball which is in a vacuum will go to a higher height because there's no resistance. It will go to a higher height. So it is going to go to a greater maximum height. So H is greater. And of course, because H depends on S equals to UT plus a half AT squared, and S is greater, it means T is also going to be greater. Therefore, it's going to take more time. So T is going to be greater. Then this one, it's going to move to a shorter height because of air resistance. It stops to a shorter height. So its value of H is going to be less. It's going to stop to a smaller value of H. And because it stops to a smaller value of H, then time is also going to be less. It takes a very short time to reach the maximum height because the forces acting here, we have the weight, there's no air resistance. The resultant force here is only equal to the weight. Here there is a weight, and there is also the force due to air resistance, which is the drag. The resultant force here is the weight plus the drag. Because the resultant force here is greater, F is greater, but in the opposite direction, then the deceleration is greater. F is greater. So greater deceleration. That means it will take a short time to reach the highest point. So ball X reaches a greater maximum height and in a longer time than ball Y. So that is correct. The rest are going to be automatically wrong. Because there is no resistance for ball X, it will go to a higher value of H, and this is going to take it more time. Because there is resistance which acts in the opposite direction to motion for ball Y. Remember, motion is upwards. Motion is upwards for both. So, because motion is upwards, for ball Y, the resistance or the drag force is downwards, adding up to the weight, giving a bigger, greater resultant force which is downwards, yet motion is upwards. A bigger resultant force in the opposite direction to motion gives a bigger deceleration. So it takes a very short time to reach the highest point. So here the answer is automatically A. The graph shows the variation of velocity with the time for a stone that falls from a bridge into a lake and sinks to the bottom. It sinks to the bottom. What can be deduced about the motion of the stone? Note that this is a velocity against time graph. So the gradient gives the acceleration. So we know that the gradient is the acceleration. Gradient equals to the acceleration. So here we are seeing that the gradient is decreasing. So here the acceleration is decreasing. So acceleration is decreasing, which means it is falling in air. So here it is in air. Then here it rapidly decelerates. It rapidly decelerates, or the velocity decreases very fast. So here it must have been hitting, it must be in water. It must be in water. And here it must have reached what we call terminal velocity. Terminal velocity. Here the acceleration was decreasing because of air resistance. That is, the gradient was decreasing. Then here the velocity decreases rapidly. The velocity decreases because now the resultant force, which is now going to be the upthrust, plus the resultant force upwards, which is the upthrust, is very big. Then now it moves at a constant velocity when the upthrust is equal to the weight of the object, plus maybe the drag. So what can be deduced about the motion of the stone? Terminal velocity was reached in air. In air, we are not seeing a constant velocity, so that is not true. The acceleration was still decreasing, but had not reached zero. The acceleration in air was decreasing with increasing time. I think we see that the gradient keeps on decreasing. The graph is showing that the graph is showing a decreasing gradient. So graph shows a decreasing gradient. The decreasing gradient shows that the acceleration was decreasing, so the answer is B. The graph shows the variation of the momentum P with the time T for a car. What is the resultant force on the curve at t equals to 10 seconds? So t equals 10 seconds is somewhere here, and here we have a straight line. And this is a graph of momentum against time. Resultant force equals the rate of change of momentum, which is the gradient. Because between 0 and 20 the gradient is constant, it means the resultant force at 10 is the same as the resultant force along this line. So the resultant force is going to be equal to the change in momentum, which is 4 minus 1 times 10 to the power of 4 divided by 20. So 3 exponent 4 divided by 20, that's 1,500. So the resultant force is 1,500 newtons. Two objects X and Y form an isolated system. X and Y collide and then separate. The mass of X is greater than the mass of Y. Which statement about the collision is correct? So the mass of X is greater than the mass of Y. and they are forming an isolated system. That means total momentum before collision is equal to total momentum after collision. That means the change in momentum for x and the change in momentum for y should be equal but opposite, because total momentum before collision should be equal to total momentum after collision. Okay, so which statement about the collision is correct? The change of momentum of y is greater than the change of momentum of x. They should be equal. So they should be equal but opposite. According to the law of conservation of momentum, equal but opposite. If we combine the law of conservation of momentum with the Newton's third law, the change in momentum of y is equal but opposite to the change in momentum of x, according to Newton's third law. Then the force on y is greater than the force on x. By Newton's third law again, the force should be equal but opposite. So they should also be equal but opposite. The force on x, that x and y exert on each other act for the same length of time. Of course, when they're in contact, the time of contact is the same. So the answer is going to be C. Remember, force on x is equal to the negative force on y. The negative just shows opposite direction. The change in momentum of x is equal but opposite to the change in momentum of y. The time of contact is always the same because force is equal to the rate of change of momentum, and T for x and T for y is the same. So the answer is B. Which law states whether total momentum and total kinetic energy are conserved in an inelastic collision in which there are no external forces? So inelastic kinetic energy is not conserved, but total momentum is always conserved. So as long as the collision is elastic, because there are no external forces acting, the collision, as long as the collision is inelastic, total kinetic energy is not conserved. So kinetic energy is not conserved, so the answer is going to be B. Total momentum is always conserved, whether the collision is elastic or inelastic, as long as the system is isolated, as long as there is no external forces acting. A tennis ball is thrown vertically upwards. The tennis ball reaches its highest point and then falls back to the ground. So I'll try to sketch this here. It is thrown vertically upwards. So it goes to the highest point and then comes back to the ground. Okay. At which position on the path of the tennis ball is the resultant force on the tennis ball greatest? When it is just being thrown, it is thrown vertically upwards. The tennis ball reaches its highest point and then falls. At the highest point, of course, it is, they said air resistance is not negligible. So the resultant force, remember, it has a weight which is vertically downwards. The weight is vertical downwards. When motion is upwards, the drag force is downwards. Before being thrown, the drag force is equal to 0. So the resultant force is equal to the weight. When it is going upwards, the drag force, of course, it decreases. The resultant force, this side, the resultant force is going to be equal to the weight plus the drag, in this case, when it is moving upwards. When it is moving downwards, on the right hand side, the resultant force is going to be the weight minus the drag, because the weight is downwards, and when it is falling, the drag force is going to be upwards. Of course, at the highest point, the body momentarily stops. So at which point on the path of the tennis ball is the resultant force on the tennis ball greatest? So A, at the start, just after the tennis ball is released, just after it is released, the drag force is going to be 0, so the resultant force is only going to be the weight. Then at the highest point, remember the drag force was decreasing as it goes to the highest point, and at the highest point, because air resistance. So one thing I want us to note is that when it is at the highest point, it momentarily stops. So at the highest point, the resultant force is equal to the weight. But at this point, when it is just released, when it is just thrown upwards, for it to move vertically upwards, then the force applied must be greater than the weight and also the drag force. The force applied must be greater than the weight and also uh, the drag force. But of course, the drag force is initially 0. So that means the resultant force at the point of just releasing it is going to be greater than the sum of these two is going to be greater than the weight, is going to be greater than drag. Therefore, at the start, when it is just being released, is given a force which is going to cause it to move against gravity, but of course that force decreases because the drag force and the weight will now be the only forces acting when it is in air. So the answer is going to be A. Which statement correctly describes a cupoid? Remember, a cupoid, the forces should have the same magnitude or same size. They should be in opposite directions. Their lines of action should never meet. Lines of action should never meet. In other words, the forces should not be in the same line. And of course, the resultant force should be 0, but they should cause rotation. The torque should not be 0 because the cupoid causes rotation. So a cupoid is a pair of forces that act in the same direction. That is not true. A cupoid is a pair of forces that act on the center of gravity of the object. So that means they will be acting through the same point. That is not true. A cupoid is a pair of forces that act to produce a resultant force. A cupoid produces 0 resultant force. A cupoid is a pair of forces that act to produce rotation only. So they cause rotation because the resultant torque is not 0. So the answer is D. A uniform beam of mass 1.4 kilograms pivoted at P as shown. The beam has a length of 0.6 meters and P is a distance of 0.2 meters from one end. Loads of 3 kilograms and 6 kilograms are suspended at distances of 0.35 and 0.15 from the pivot as shown. Note that the beam is uniform, so its weight is at the midpoint. So here where we have the mass of the beam must be the center of the beam. And this distance here is going to be half of 0.6, which is 0.3. So that is 0.3. Then this distance here, that distance is going to be 0.4 minus 0.3, which is 0.1 meters. What is the torque that must be applied to the beam in order to maintain equilibrium? So let's try to find the clockwise moment. I'll get the clockwise from this side because this is causing clockwise. That is, I think that is the only one causing clockwise. Let me get to on the right hand side. So clockwise moments is going to be 6 times 9.81 to change it to force. So that is mg. Then times the perpendicular distance from the pivot is 0.15. 6 times 9.81 times 0.15. So that is 8.29. Yes, it is 8.829. That is Newton meters. That's clockwise moments. Then anti-clockwise moments, I will do the anti-clockwise moments this side. Anti-clockwise moments, we have the weight of the beam, and then we have this mass here. So we have 3 times 9.81 to change it to mass, that is mg. Then times the perpendicular distance of 3, which is 0.35, then plus 1.4, then times G, which is 9.81, times the perpendicular distance, which is, I think it is 0.1. So this is going to be equal to 3 times 9.81 times 0.35 plus 1.4 times 9.81 times 0.1. So this is 11.6739 Newton meters. So the resultant torque is going to be 11.6739 minus 8.829. So minus 8.829. So that is 2.8 Newton meters. So to maintain equilibrium, we need an extra 2.8 Newton meters. So that is D. The diagram shows three rigid objects P, Q, and R subjected to different combinations of forces. Which object is in equilibrium? So for equilibrium, resultant torque should be 0. Resultant force should also be 0. So let's check this one here. So here, resultant force is 0, but the resultant torque is not equal to 0 because this is causing clockwise moments. The clockwise rotation is caused by 20 newtons, and the anti-clockwise moment is caused by the anti-clockwise rotation is caused by 10 newtons, and yet the perpendicular distances are the same. That means the torque is not equal to 0. There is a resultant. So there is a resultant which is clockwise. There's a resultant torque clockwise. So that means P is not in equilibrium. So wherever I see P, I just cross it out. Then let's check Q. For Q, the resultant force, we have a resultant this side, which is going to be 20 newtons. That is 80 minus 60. We also have a resultant here, which is also going to be 20 newtons. So there is a resultant of these two, which is going to be vertically upwards. So there is a resultant force upwards. So Q is not in equilibrium. So Q, wherever I see Q, it's not in equilibrium. So I will just say none of them. None of them. I don't even need to check R because for Q there is a resultant force upwards. The diagram shows two liquids labeled P and Q that do not mix. The liquids are in equilibrium in an open tube. Three equal distances x are labeled. What is the ratio density of P over density of Q? So at the same level in the liquid, the pressure at that point is the same as the pressure there. The pressure here is going to be due to the height of the liquid x, and the pressure here is going to be due to the height of this liquid, which is going to be 2x. So pressure is equal to density times G times H. And pressure at this point is the same as the pressure at this point in the same liquid. Therefore, the pressure at this point here on the left-hand side is going to be the density of the liquid above, which is going to be, let's say, liquid P. So I will say density of liquid P times G. The height is 2x, so that is times 2x. Should be equal to the density of liquid Q times G, and the height is x. So G cancels, x cancels. So we want a ratio of density of P over density of Q. So density of P over density of Q is equal to 1 divided by 2, which is a half. So the answer is A. So the answer is a half. The density at the pressure at the same level in the same liquid is equal. That's why I equated left-hand side to the right-hand side. A stone of mass 0.3 kilograms thrown vertically downwards with a speed of 20 meters per second from a height of 12 meters. It falls vertically until it hits the ground. Air resistance is negligible, which means we can use the equations of motion. What is the kinetic energy of the stone just before it hits the ground? So I'm going to find the speed. So using v squared equals to u squared plus 2as, I'm going to find the speed with which it hits the ground. So it is thrown vertically downwards with that speed. So this is going to be 20 squared. Because it's thrown vertically downwards, the acceleration is not negative. So this is going to be plus 2 times 9.81. Then it follows through a distance of 12 meters. So v squared is going to be equal to 20 squared plus 2 times 9.81 times 12. So that is 635.44. So this is v squared. So kinetic energy is a half m v squared. So this is going to be a half. The mass is 0.3. Then v squared is 635.44. I don't need to square this because this is v squared. So I'll just say that times 0.3 divided by 2. So this is giving us 95.3 or approximately 95 joules. So the answer is going to be D. A student can run or walk up the stairs to her classroom. Of course, it means running takes a shorter time, walking takes a longer time. The distance is the same work is going to be done. So this is short time, walking takes longer time. Okay, which statement describes the power required and the gravitational potential energy gained while running up the stairs compared to walking up them? So power is work done divided by time taken. The work done is the same because the work done is the same. The work done is going to be equal to the gain in gravitational potential energy. So this is going to be the gravitational potential energy gained divided by T. T is smaller because the work done is the same. W is the same, and yet power is inversely proportional to T. So the one which takes the one with a shorter time results into high power. So running provides more gravitational potential energy? Not at all. The gravitational potential energy is the same because the work done is the same. So the work done is the gain in gravitational potential energy. So it's going to be the same. The running provides the same gravitational potential energy, which is true, but then running provides more power because the time is smaller. So running provides more power because the time is smaller. So the answer is C. So running uses more power. A weight W hangs from a trolley that runs along a rail. The trolley moves horizontally through a distance P and simultaneously raises the weight through a height Q. So if I want the gain in gravitational potential energy, it's simply going to be mgh, which is going to be the weight of the trolley is W times the height, which is Q. So as a result, the weight moves through a distance r from x to y. It starts and finishes at rest. How much work is done on the weight during this process? So the work done on the weight is equal to the gain in gravitational potential energy, which is simply going to be mgh, which is going to be W times Q. So R and P do not contribute to the work done against the weight, the work done on the weight. So the answer is going to be just C. The equation for kinetic energy can be derived using the equations of motion. 4 equations relating to motion are listed. So we know that the kinetic energy can be obtained from the work done. In other words, work done is equal to the work done is equal to the gain in change in kinetic energy. And of course, we know that work done is equal to force times distance. So this one is used. And the force is equal to mass times acceleration. This one is used. How do I find the acceleration? From v squared equals to u squared plus 2as. The acceleration is going to be v squared minus u squared divided by 2s. So this equation is also done, is also used. So this one will not be used at all. So which 3 equations can be used to derive the equation EK? The equation because kinetic energy is equal to a half m v squared. And I can show you how we derive this. So from work done equals to force times distance, the work done is going to be equal to ma times s. And where there is a, I'm going to put v squared minus u squared over 2s. So this is m into v squared minus u squared over 2s, then times s, and s cancels. So this is going to be mv squared over 2 minus mu squared over 2. And this is equal to the change in kinetic energy. If this starts from rest, then this part would be 0. So it is 1, 2, 3. 1, 2, 3, which makes the answer to be A. The force extension graph of a metal wire is shown. At which point on the graph does the metal wire stop obeying Hooke's law? Hooke's law stops on the straight line. So Hooke's law stops on the straight line. That means the answer is going to be A. Hooke's law is obeyed where the straight line stops. So that means the answer is going to be A. So straight line stops. That's where Hooke's law stops being obeyed. A uniform wire is made of a metal that has Young modulus 1.3 times 10 to the power of 11 pascals. The wire is 2.4 meters long and has a spring constant of 2.7 times 10 to the power of 4 and newtons per meter. What is the volume of the wire? Okay. So of course we know that Young modulus is equal to the stress, which is force over area, over strain. When I get the reciprocal, it's original length over. So the stress is force over area, then original length over extension. But they said it has a spring constant of that. We know that F over extension is equal to the spring constant. So Young modulus is going to be equal to the spring constant times L over area. Okay. And also, I'll use this side now. We know that volume equals to cross-sectional area times length, which means the cross-sectional area is going to be the volume divided by L. So it means the Young modulus E is going to be KL. Where there is area, I'll put V over L, which means Young modulus is going to be KL squared divided by the volume. Now I'm going to make volume the subject and substitute. So V is going to be K, which is 2.7 times 10 to the power of 4, times L, which is 2.4 but squared, divided by the Young modulus. I'm making V the subject, so divide by E, which is 1.3 times 10 to the power of 11. So 2.7 exponent 4 times 2.4 squared divided by 1.3 exponent 11. So that is 1.2 times 10 to the power of minus 6. Meters cubed. So the answer is going to be D. A rubber cord hangs from a rigged support. A weight attached to its lower end is gradually increased from 0 and then gradually reduced to 0. Okay. The force extension curve for contraction is below the force extension curve for stretching. So stretching, this is contraction. Contraction is unloading. Then the area under the whole of this is loading. The area just under the lower part is going to be unloading. Okay. What does the shaded area that between the curve represents? Of course, the shaded area is the difference between the work done in stretching and the work which is returned during unloading, and that is the energy which is dissipated as thermal energy. So that is the thermal energy which is dissipated in the rubber cord, which warms up the rubber cord, which is going to be B. The energy which is retained during unloading, which is not returned during unloading, that is the thermal energy dissipated in the rubber cord. A source of sound waves of constant frequencies traveling as shown. In which situation would the stationary observer detect a sound with the lowest frequency? First of all, lowest frequency, it should be away from the observer. The source should be moving away from the observer. Lowest frequency, it should be away from the observer. This one is showing towards, so this is out. This is also showing towards, this is also out. Now C and D are showing away. But remember, the observed frequency is equal to V over V plus the speed of the source times Fs. Now the lowest frequency will depend on the speed. The one with the highest speed is going to be having the lowest frequency, and the answer is therefore going to be D, because the speed Us is larger for D compared to that for C, which makes the denominator even much bigger compared to that for C. So the observed frequency is going to be lowest in part D. So the answer is D. Each of the principal radiation of the electromagnetic spectrum has a range of wavelengths. Which wavelength is correctly linked to its radiation? So remember, we said Reed's mother is visiting Uncle Xavier's garden. And we know that for visible light, visible ranges from red to violet, where red is 7 times 10 to the power of minus 7 meters, and violet is 4 times 10 to the power of minus 4 meters. So the infrared must have a wavelength higher than 7 times 10 to the power of minus 7. That could be around 10 to the power of minus 6, 10 to the power of minus 5, and so on and so forth. And microwaves should have a wavelength which is about 10 to the power of minus 3, 10 to the power of minus 4, around there. So it means this cannot, microwaves 10 to the power of minus 5 is approximate infrared, so this is out. Then on the other side, ultraviolet should have a wavelength which is lower than 10 to the power of minus 7. It could be around 10 to the power of minus 8, minus 9, and so on and so forth. So this could be UV. So the answer is UV. The wavelength here is around 10 to the power of minus 8. This is around 10 to the power of minus 11. This is around 10 to the power of minus 13. So the answer is going to minus 14 minus 13, that is gamma rays. So this one is not correct also. X is around 10 to the power of minus 11, or at most minus 12. Or at least minus 12, not at most. A transverse water wave has a frequency of 15 GHz, a wavelength of 0.12 meters, and an amplitude of 4 millimeters. P is a water particle that is initially at the peak of the wave as shown. What is the total vertical distance traveled by P in a time of 0.5 seconds? So the first thing I'm going to find is the period, time for one cycle for that particle. So period is 1 over 15, which is going to be equal to, okay, let me leave it as 1 over 15. Then how many cycles will the particle have made in 0.5 seconds? One cycle is this time. So number of cycles is going to be 0.5 divided by the period, which is 1/15. So 0.5 divided by 1 divided by 15. So that is 15/2, which is 7.5. So this is going to be 7.5 cycles. So P will have made 7.5 cycles in that time. Now, one cycle, if it makes one cycle, from that point it should go to equilibrium, that is amplitude. It goes downwards, that is also amplitude. Then it comes back, amplitude. Then it comes back, that is amplitude. That means one cycle has 4 parts of the amplitude. So one cycle is equal to 4 times the amplitude. So the question is, what is the total vertical distance traveled by P in a time of 0.5 seconds? So because it makes 7.5 cycles and one cycle is 4 times the amplitude, then total distance is going to be equal to 7.5 cycles, and one cycle is 4 times the amplitude, which is 4.0, and this gives us 7.5 times 4 times 4, which is 120 millimeters. So the answer is C. A wave is formed on a string. A student plots a graph of the variation of the displacement d with the time t on the string. The student marks 2 points x and y on the graph. Which property of the wave is represented by the distance along the horizontal axis labeled x? So this point here and this point here are in phase. They have reached the same distance. They have moved the same distance. They have the same displacement. So xy must be the wavelength. So the answer here is automatically, sorry, this is t, displacement against t. So that is not wavelength. That is going to be the period. Because it's a graph of displacement against time, then this is going to be time for one cycle, which is going to be the period. A stationary wave is set up in a stretched string. Which distance is equal to the wavelength of the wave? We know that in a stretched string, if a stationary wave is formed, if you have a stationary wave formed on a string, the distance between a node and the next node is always half wavelength. That is, distance between one node and another node, the next node is always half wavelength, which means the wavelength is going to be twice the distance between a node and a node, or twice the distance between an antnode and an antnode. So let's see the options. Double the distance between adjacent antinodes. If this is an antnode and this is an antnode, still the distance between two adjacent antinodes is half wavelength. This is half of a cycle. So this is also twice distance between an antinode and an antinode. So the answer is going to be A. A source of coherent light is incident on two slits P and Q, which are placed 80 millimeters apart. The light has a single frequency of 1.5 times 10 to the power of 12 Hz. The light from the slits meets on a screen that is a distance of 4 meters from the slits. The screen is parallel to the line joining the slits. An intensity sensor is placed on the screen at the midpoint of the intensity of the interference pattern such that the intensity reading is maximum. So let's say this is the midpoint and the intensity is maximum. The intensity sensor is moved along the screen. The sensor travels through two intensity minima. So let's say this is an intensity minimum and another, let's say this is an intensity minimum and another intensity minimum. Of course, there should be maximum. So this is a minimum, maximum, minimum. So it moves through two intensity minimum and two intensity maxima. So this is one maximum, then another one. And two intensity maximum and stops in the middle of the third intensity minima. So I have to add another intensity minima here. Okay. Which distance does the sensor move through? So it moves through, this is x plus x plus a half x. So that is x plus a half x. So because the distance between two successive maxima is x, so it moves through x plus half x. We just need to find x. So let's find x. So we know that the wavelength is equal to ax divided by d, which means we need to find the wavelength first. They gave us the frequency and they told us this is a source of light. So the wavelength is going to be v over f. V is 3 times 10 to the power of 8 divided by f, which is 1.5 times 10 to the power of 12. 3 exponent 8 divided by 1.5 exponent 12. So that is 2 times 10 to the power of minus 4. That is the wavelength. So x from the first equation, x is equal to lambda times d divided by a. Lambda is 2 times 10 to the power of minus 4. D is equal to 4 meters, the separation, that is d. Divided by a, that is 80 times 10 to the power of minus 3. Answer. So that is times 4 divided by 80 times, 80 exponent minus 3. So that is 0 0.01. So this is 0 0.01. That is in meters. In millimeters, I will multiply this by 1000. That is 10 millimeters. So x is 10 millimeters, but total distance is 10 plus 10 plus 10 over 2, which is 25 millimeters. That is x plus x plus x over 2. So the answer is C. A vibrating bar produces surface water waves in a ripple tank. The wavelength of the waves is 5 centimeters and they pass through a gap of width 20 centimeters. So we notice that the width is much bigger than the wavelength. So the diffraction is minimum, is less. Which change will increase the amount of diffraction that is observed? So either, because the width is greater, we have to reduce the width decreased, or we increase the wavelength by all means to make them closer, because diffraction is maximum when the width is approximately equal to the wavelength. That's when diffraction is going to be maximum. So to increase diffraction, we should make one to be close to the other. So decreasing the distance between the bar and the gap, that one has no effect on the diffraction patterns. Decreasing the frequency. If we make the frequency decreased, we are going to be increasing the wavelength. And if we increase the wavelength, it will be getting closer to the size of the gap. So this is going to increase the amount of diffraction. So the answer is going to be B. So decreasing the frequency increases the wavelength, and when it is close to the size of the gap, then diffraction has increased. What is an electric current? We know that current is the rate of flow of charge carriers. Current is the rate of flow of charge carriers. So it is a flow. It's a flow of current is a flow of electric current is not an electron. It's not the charge on the particle. It's not a flow of energy. It's a flow of charge carriers. That's electric current. The rate of flow of charge carriers is electric current. A wire of diameter d is connected into an electric circuit. There is a current I in the wire and the charge carriers have an average drift speed V. So there is a current I. The equation which relates to this is I equals to never. Okay. The average drift speed is V, the diameter is D. Of course, we know that area equals to pi d squared over 4. So the equation now becomes I equals to N E V times pi d squared over 4. The wire is replaced with a new wire of the same material. That means N is the same, of course E is the same. Same material, N and E are going to be the same, but with a different diameter. So the new current is going to be I'll call it I2, is going to be, because this same material N is the same, then times E. The drift velocity is 3v, so this is going to be times 3v, then times pi. Where there is d, I'll put 0.5d, but this is squared, then divide by 4. So it means I2 is going to be N E times 3v times pi times 0.5 squared d squared divided by 4. So I have this equation here and I have this equation here. What is the current in the new wire? So the answers are in terms of the first one, so I'm just going to divide the two equations. So I2 divided by I is going to be NE times 3V times pi times 0.5 squared times d squared over 4 divided by NE V pi d squared over 4. So d squared over 4 cancels out, pi cancels, V cancels, N cancels, E cancels. So I remain with I2 over I being equal to 3 times 0.5 squared. 3 times 0.5 squared, which is 3 over 4. So this is 3 over 4. And I think this is the same as 0.75. So I2 is equal to 0.75 I. So the answer is going to be A. A fixed resistor and diode are combined by connecting them in series. So you have a fixed resistor and a diode. By combining them in series, the total potential difference across the combination is varied and the corresponding current I is measured. So the total potential difference across them is going to be V. It is varied. And the corresponding current I is measured. Which graph could represent I with V? Of course, a diode conducts at a certain voltage. When V is less than, a diode conducts at a value which is approximately 0.5 volts for some diodes. So a diode will not conduct at values close to 0. Therefore, for values close to 0, because the diode does not conduct, then the current is going to be 0. So for values of V close to 0, the diode does not conduct. So for values of V close to 0, the diode does not conduct. So I equals to 0. So it means we ignore B and we ignore C and we ignore D. This is showing that there is no current and there is no voltage, and all of a sudden the voltage starts from a certain value, and when there's a voltage when the current is 0, but there's no current when the voltage is low for a diode. So this part here, the diode is not conducting, but after it is energized, now it can conduct. Remember, a diode is made up of a semiconductor. So the answer is going to be A. The potential difference across a fixed resistor is V. The power dissipated in the resistor is 5 watts. The PD across the resistor then changes to a new value. With the new PD, the energy transfer to the resistor is in a time of 2.25 seconds is 45 joules. What is the new PD across the resistor? So for the first part, we know that power equals to V squared divided by R, which means the power was 5 equals to V squared divided by R. That is going to be the first equation. Then for the second equation, or I can say, let me just say 5R equals to V squared. That is one equation. Then here they have given us energy. And we know that energy equals to power times time, which is going to be, I will call this one the second PD, which I will call V2 squared over R. The resistance here has remained the same. Then times time, which is T. So this means when I make V squared again, the subjects of V2 squared is going to be equal to the energy times R divided by T. That is V2 squared. I substitute. This means V2 squared, the energy is 45 times 2.25. Then the time is, where is the time? Sorry, that is energy is 45 times, sorry, this is resistance. Energy is 45, resistance is R divided by the time, which is 2.25. Okay, so I'm going to combine the two equations by just, this is going to be my second equation. I'm just going to divide. So V2 squared over V squared is going to be equal to 45R over 2.25 times the times 1 over 5R, because I'm dividing. So R cancels, by 5 1, by 5 9. So 9 divided by, so I just get the square root. 9 divided by 2.25. Then we find the square root of the answer. So that is 2. So it means V2 over V is equal to 2. V2 over 2, V2 over V is equal to 2, which means V2 is equal to twice V. So the answer is going to be B. The diagram shows part of a circuit that uses a potentiometer wire to measure potential difference in an external circuit. The potentiometer wire XY has length L1. It is connected to a cell of known EMF, and that has negligible internal resistance. So the PD per centimeter for this one would be E divided by L1. So that would be a constant. The driver cell is EMF E, length is L1. Terminals P and Q are connected to the external PD to be measured. So the external PD, which is the PD across PQ, is the same as the PD across XY, which would be the same as the length L2, the balance length L2 times the constant K. Or this could be the same as L2 times E over L1, or L2 over L1 times E. Okay? The ratio of the lengths L1 and L2 is used to determine the PD between P and Q in terms of E. Which condition must be met in order to determine this PD? Of course, in order to determine this PD, to get the balance length, the resultant current through the galvan, of course, we would put a voltmeter here. The resultant current through the voltmeter should be 0. Therefore, it means I2 should go to 0. So the current I1 must be 0. That's not true. The current I2 must be 0. That would be true. So the answer is going to be B. The PD across YZ must be 0. That is not correct. It doesn't make any sense. The resistance of the external circuit must be 0. The resistance of the external circuit must be 0. So then where will the PD be? The diagram shows a circuit. Which statement about the circuit is not correct? EMF or electromotive force is the energy transferred per unit charge. EMF is the energy transferred per unit charge. I think that is a correct statement. Energy transferred from chemical potential energy in the cell to other forms when the switch is closed. Energy is transferred from chemical potential. Of course, in the cell, we have chemical energy is transferred to electrical. That is true. The electromotive force of the cell is greater than the terminal PD when the switch is closed. When the switch is closed, the EMF is equal to the terminal PD plus the lost volts. That is also true. So it means the answer is D. That's not correct. When the switch is open, the voltmeter measures the EMF of the cell. If the cell has internal resistance, when the switch is closed, V would be equal to the EMF minus the lost volts. So the voltmeter does not measure the EMF, so that's not a correct statement. A circuit contains a battery of EMF E, an internal resistance R connected to two resistors, each of resistance 2.5 ohms. The resistors are connected in parallel. Okay. The current in one of the resistors is 0.8. Now these are identical resistors. So if that is 0.8, this should also be 0.80 amperes. And it means total current flowing through the battery is going to be 0.8 plus 0.8, which is 1.6 amperes. That is the current through the battery. Which expression where E is in volts and R in ohms gives the internal resistance? Okay. Let's first find the PD across each of these, the PD in parallel. The PD here is going to be equal to I times R, which is going to be 0.8 times 2.5. I think this is 2 volts. So this is the PD across these 2 points is 2 volts. PD in parallel is 2 volts. And that is going to be the terminal PD. So the EMF equals the terminal PD plus the lost volts. So the EMF is E, the terminal PD is going to be 2 plus the lost volts, which is current times internal resistance. So the EMF is E, which is equal to 2 plus the current is 1.6 times internal resistance R. Making R the subject, R is going to be E minus 2 divided by 1.6, which makes the answer to be C. What is the rest mass of a beta particle? Of course, a beta particle is a fast-moving electron, and an electron has a mass of 9.11 times 10 to the power of minus 31 kilograms. So the answer is B. What is the name of the group of particles containing mesons? Mesons are hadrons. And the name of the group of particles containing baryons. Baryons are also hadrons. So, group of particles containing mesons, those are hadrons, they are not leptons. Baryons, those are hadrons, they are not leptons, so the answer is A. A magnesium nucleus decays by emitting two particles. So magnesium 2312 decays by emitting two particles, resulting into sodium 2311 plus two particles. Which two particles are emitted? Now notice that the proton number is already 11 here, so this should be 1. The nucleon number is 0 here, so this is a beta plus. Because our proton number is 1, nucleon number is 0, that is a beta plus. And the beta plus is normally accompanied by a neutrino. So the particle is a beta plus, not an alpha, not beta. The particles are going to be beta plus, not alpha. It's not going to be alpha, it is beta plus, which is accompanied by a neutrino. Beta plus accompanied by a neutrino, so the answer is D. Okay, so that is the end of the multiple choice of October, November 2024. See you in Feb March papers. Until next time, bye bye.